Hello and welcome to this tutorial on probabilistic programming. This is a tutorial from a categorical perspective. It's part of a workshop on categorical approaches to probability and statistics. By the way, if you're looking for a more traditional approach to probabilistic programming, there are plenty of other great tutorials out there, so I'll put them in the description below if I can. The key point of probabilistic programming is to write complex models in statistics by writing programs, so that the complexity of the model is controlled by the traditional ways of controlling complexity in programming language theory. The models are kept separate to some extent from the inference methods that are used. There are lots of probabilistic programming languages out there. One of the earliest ones was Bugs. That's still in quite wide use. Another very popular language right now is Stan. And there's currently lots of ongoing work on new languages, new approaches to this, which I put on the right-hand side. So there's a very busy field. A third key point for probabilistic programming from the categorical perspective, though, is that the probabilistic programming language itself is a sort of synthetic measure theory. That's to say, we can, to some extent, think of probabilistic programs as describing measures, and the types that we use when we're composing probabilistic programs as spaces. And to some extent that matches up with the traditional formulation of sigma algebras and measurable spaces. But we can also view it from this categorical angle where we're looking at what things we can compose and we can build. So in this tutorial, I'm going to go through 4 different things. I'm going to focus to begin with just on generative models. And we'll see generative models from a categorical perspective in terms of morphisms. I'll then talk about conditioning with likelihoods, and I'll talk then finally about a category of S-finite kernels, which I think is a very good foundation for probabilistic programming. So let's start with talking about generative models as morphisms. Here's a regression problem. That's what I want to use as my motivating example to start with. And in a regression problem, you have some points, and you want to know which function probably generated these points. Now, I'll focus to start with on linear regression, then we're asking which line probably generated these points here. These points don't all fit on a line, they're not collinear, so it can't be that they are exactly fit onto a line. And so what we want to say is that these are maybe noisy observations of a true function that generated them on a line. And then the Bayesian way of doing regression, we don't just ask for a line of best fit in some sense, we ask for a distribution over lines that could have generated them, or more generally, a distribution over functions that could have generated these points. Okay, and so what I'm showing here on the screen is a posterior distribution over what lines could have generated these points. Okay, and I'll show you in a second a program that I can easily write to get this kind of posterior distribution. So let's look at this problem for a second, but I'm going to look at it from a generative way. I'm going to be a bit casual about conditioning until we get to the later part of this tutorial. Okay, so here's this generative model, and what sort of information do we have here? Well, we have, the intercept of the line. I'm going to call that B. We have the slope of the line, which is, the gap between the intercept and its value at 1. I'm going to call that A. The gradient, and then I have all these points, and I have the values of these points and also the value of the function at these points. Okay, so for example, I can look at the third point, which is f of 3, and I'm going to call that observation point y3. It's different from the actual value of the function at 3, which I'm going to call f3. Okay, I'll similarly just label the y-coordinate of f at 4, the y-coordinate of the observation point at 4, which is different from the actual value of the function at 4. Okay, so I've got A, B, y3, f3, y4, and f4. Okay, I've also got this noise amount, the amount by which the points differ from the line, and I'm going to call that V. I'm going to be interested in the sort of the variance of that. Okay, so these are all things I want to build into my generative model. So over on the right hand side now I've put a probabilistic program that would generate them, but let's first write down a statistical model that would generate them in a sort of more traditional statistician's notation. A statistician might write A is normally distributed with mean 0 and variance 9. I don't really know what A is, but it's around like this. B I also don't know. Let's say F3 and F4 are, well, F3 is 3A plus B, and F4 is 4A plus B. And then the variance, let's say, is inverse gamma distributed. Let's say with some parameters like this. I don't really want to go into the inverse gamma distribution, but it's a good choice of a distribution for a variance. And then finally, y3 and y4 are not the true values of f, that would be f3 and f4, but y3 is rather normally distributed around the true value with the variance that we're talking about. And similarly for y4. Okay, so on the right hand side then I've got a traditional statistical model. On the left hand side over here in this box here I've got a probabilistic program, and you can see it looks extremely similar to the model, except it's written in a sort of a very clear programmatic syntax. Okay, so just exactly the same. I've got the normal distributions, I've got f3 and f4, my variance, and I'm observing my y3 and y4. Okay, so because I'm writing it as a generative model, I'm not distinguishing just now between the A and the B, the parameters that I want to infer, the slope and the intercept, and the values that I want to observe, which are y3 and y4, and also y0, y1, y2. You know, I'm just looking at y3 and y4 for now to keep it simple. Okay. But we'll come to inference in a minute. Let me, though, have a categorical angle on this program. Okay. What I could do to this program is look at its data flow graph, which is what I get by ignoring the actual order that the lines are written in the program, and instead just looking at which bits of the program depend on which other bits. That's the data flow, the way the data flows through the program. So for example, F3 depends on A and B, so I've got this arrow here from A going into computing whatever F3 is. Okay. Yeah, so that's a graphical description of the program. Now, what I want to do now is explain how this data flow graph can be understood as a morphism in a category. One thing we might want to know is whether we can rearrange the nodes of the data flow graph as the topology suggests. And the answer is going to be yes, okay, but there's a little bit of work to do to check that that is indeed the case. Okay, but so before we do that, let's talk about what the nodes in this data flow graph are. And what they are is they're probability kernels. Now, a probability kernel is a function which takes some parameters and gives you back a probability measure. So I'm wondering if I should explain what measures are a little bit. Let's do that. Here's a little bit of motivation for measures. I'll be very brief. You'd better look it up if you've got no idea at all. Okay, but basically when we're talking about probabilities on the real plane, then there's the chance of getting any individual number is often 0. Okay? Think of the game of darts. Here I've drawn in black the areas that would score me 20 points. So if I wanted to get 20 points, what would be the chance of getting that? Well, I could talk about hitting one of these areas. What I couldn't do is talk about hitting the very centre of the bullseye, or hitting a particular point on the dartboard. Okay, so instead of talking about hitting particular points, I talk about landing in regions, and that's exactly what measurable spaces give us, this kind of ability to do that. So a measurable space comprises a set together with a sigma algebra, which is a set of subsets that's closed under countable unions and complements, and those are going to be the events, those are going to be the things that we can assign probabilities to. Often the singletons will be in the sigma algebra, but there'll be lots of other sets in there too. And a typical sigma algebra is one that's generated by the open intervals of the reals and then closed under countable unions and complements. So that then a probability measure on a measurable space is a function that assigns to every event, every element of the sigma algebra, every set in the sigma algebra, a probability. in such a way that probabilities sum to 1 over all, and also in such a way that when we take, let me write this down, so when we take the probability of a disjoint union of a family of sets, it's the same as taking the sum, this is called sigma additivity, of probabilities. Okay, so that's a measurable space and a probability measure, but a probability kernel is something which takes some parameters, x, y, and z, and gives us back a probability measure. So it must be two things. It must be measurable in the parameters. Here I've given it 3 parameters, but we could have some other number of parameters. And it must be a measure, a probability measure, in the sigma algebra of the probability of the measurable space. Okay, so the normal distribution is an example of that. It has some parameters, the mean and the variance, and it gives us back a probability measure which depends on those parameters. Okay, so the question now is to build this up in a categorical way. How do we compose probability kernels? So on the left over here, I've drawn 2 probability kernels, L and K, and I want to see how to compose them. Well, the way I do that is by saying, if I've got K and L and I want to compose them on one particular wire, one particular parameter, then what I do is I get a new kernel back, which has 3 parameters again, because actually L only has 1 parameter. But those parameters are different now. They're the parameter for L together with the other parameters Y and Z for K. And the way that we combine these two things is by integration. Measures allow us to do Lebesgue integration, and so that's how we combine 2 probability kernels. And so the result of composing these 2 probability kernels in this way is given by the probability of landing, given the parameters A, Y, Z, of landing in the event U is whatever the kernel K would tell us about X, Y, Z, and U. But where's X come from? X is supposed to have been sampled from L. So what we want to know is what's the probability of getting X. And so we integrate K, X, Y, Z, U over L with the parameter A with respect to X. So L, remember, is a measure because it's a probability kernel. So that's how we compose probability kernels. Here I'm doing it in a kind of a multi-category way, but you could also set it up as a category and then talk about a monoidal structure. I think you'll see in a second why I find it quite helpful to see it as a multi-category, but if you don't know about multi-categories, you can go and think about setting it up as a category or a monoidal category. Okay, so looking at this picture here, let me draw a composition of 3 probability kernels. I'll plug L in, but I'll also plug in M. Okay, so that's another kernel, and let's say that's going to be over a space B, and then we still have Z coming in as a parameter to K. Okay, so when we form this composition of K composed with L composed with M, well, that gives us another kernel which depends on not an A, Y, Z, but an A, B, Z. And it's going to tell us what's the probability of landing in some set U. And that probability will be found, well, just following the recipe for composing kernels, which I'll just show you what the result is. We integrate first over X and then over Y, over the second argument. And what do we integrate? Well, we need to know in the end what's K, Y, Z, U. We're first integrating with respect to the measure A. That's what the first integral, the inside integral, is integrating over. But we also need to integrate with respect to M. And M takes the parameter B. Okay, so it's an iterated integral. And one little tricky thing to show is that this makes sense. How do we know this makes sense? Well, because actually one thing to check is that this composite is still a probability kernel. In particular, it's still measurable in its parameters. Okay, that's a little thing to check, which allows us to then use it in an iterative way to compose three things. And then those of you who've done some probability before will know Fabini's theorem, which lets us reorder the integrals here. I'll just write what we get then. So we first integrating with respect to m with its parameter b, and then with respect to L with its parameter A. And this is what we would get if we composed in the other order. If we first plugged in M and then we plugged in L. And so that's why it's okay to do topological deformations to the probabilistic program when we view it as a data flow graph. So in summary, probability kernels, when we compose them, form a proper multi-category, in other words, a symmetric monoidal category. Okay, let me say a little bit more about the kinds of generative models we might consider for regression. So here what I've done is I've changed my model to include not just a slope and an intercept, but actually a program. So I've got a prior distribution over programs in some grammar, and I've written a little interpreter for programs inside my probabilistic programming language, and that gives me for each program a function. And then I've done inference again. I'll tell you about inference in a second, but I've done inference again to ask which program generated these points. And we can see here a posterior distribution over programs. And you can see inside my little programming language that I'm interpreting inside the programming language, I've got an if-then-else construct, and the program has decided the inference has decided to do the if-then-else branch. So it's something like this: if x is less than, 3.5, something like that. It's not really sure. So for each draw from the posterior, it's putting a slightly different number. But if x is less than 3.5, then we probably do a curve like one of these. Otherwise, we're going to do a curve like one of these. And these in turn are defined in the programming language that's interpreted inside the programming language. And those would be they look like quadratic functions. I don't know. It's found them from the grammar of programs. Okay, I also want to tell you a bit about other kinds of problem we could study, and that leads me on to another categorical aspect that comes up in generative modelling. So here are some points, and I want to know, do they split into clusters? One thing I've been looking at is some stuff in social science where we're looking at Twitter feeds and where hate events come up in Twitter. And maybe we want to know how could we group these hate events into clusters? Okay, so this could be a Twitter timeline of some kind. Okay, hopefully by squinting you can see that there's one cluster on the left-hand side and one cluster on the right-hand side, and we want to find these clusters in a Bayesian way. And so what we'd end up with in a Gaussian clustering model is a mixture model like this, where we have a mixture of this blue bell curve, this blue Gaussian curve, and this red Gaussian curve added together in some convex combination. So we don't know a priori either what proportion of things are in one cluster versus another. And it's very easy to set this up as a probabilistic program, as a generative model. That's what I did to generate this picture. Okay, but the black line is the most probable line of where points will lie, and we see that that's built from the blue curves and the red curves. Okay. And here's the model. So we have the locations x1 and x2 for the two Gaussians, and we have their variances. So we don't know the x1 and the x2, and neither do we know the v1 or the v2. We don't know how many things are in one cluster versus another. So let P be the number of things in the left-hand cluster, and 1 minus P be the proportion. Let P be the proportion of things in the left-hand cluster, and let 1 minus P be the proportion of things in the right-hand cluster. So that's the area under these blue curves is P. Okay. And now I'm using a programming language feature of iteration or a for loop to go over all the data points. There are n data points, and it's a generative model, so I'm not talking about inference just now. I'll just talk about how these points would be generated. And what I would do is for each point, let's say there's capital N points, I'm going to toss a coin with probability P, which is the chance of landing in the blue area, the blue cluster. And if I'm going to land in the blue cluster, then I'll generate my position on the x-axis by a normal distribution, mean x1 and variance v1. But if I'm landing in the red cluster, I'll generate my position by a normal distribution with mean x2 and variance v2. It's very easy to write this as a probabilistic programming. That's what I did here. Okay, so there's a little bit more going on here than we saw with the regression problem, in that we've got this if then else coming up, and that's a bit hard, I think, to draw in terms of string diagrams, but what we can do is understand it very easily in category theory nonetheless by saying that probability kernels don't just form a symmetric monoidal category, they actually form a distributive symmetric monoidal category, which means that we don't just have a monoidal structure which we're using to combine the wires, we also have an if then else kind of construction coming from a co-product and co-pairing in there. So 1 plus 1 is the Boolean type. That's what a Bernoulli draw gives us, and that lets us do an if then else because it has the universal property of a co-product. Okay, so that's the key point here, just to bring it to a conclusion of generative models as categorical morphisms, is that probability kernels form a distributive monoidal category. Right, the next thing I want to do is to start to talk about conditioning. So we've seen examples of inference in the programs we've looked at so far, but so far we've just been describing them as generative models, and I've been skirting over the issue of inference. So let me talk more about that. And to do that, I want to cut back to a really simple example, sort of thing you might look at in high school. Suppose I've forgotten what day it is. Here are some buses in Oxford, and what I might do to figure out what day it was would look out the window, see if there's much traffic. Let's be sort of more precise. Look out the window and count how many buses I see in a given hour. And let's say there were typically 3 buses per hour on Sundays and 10 buses per hour the rest of the week. So if I notice 4 buses per hour, is it a Sunday? So I'm going to set this up as a probabilistic program in the following way. Whether or not it's Sunday, the probability of that is a Bernoulli trial. There's 7 days in the week. I don't know which day it is, so let's say it's uniformly distributed between 1 and 7. Then I'm going to let the rate of buses be either 3 or 10, depending on whether it's a Sunday. And now I include a new construct which we haven't seen before, which is observe. Okay, so I observe 4 buses. So rather than just say that, let's say, the number of buses n is drawn from a Poisson with a particular rate, I'm actually saying what that n is. I'm saying it's 4. Okay, and then I'm interested in whether it's Sunday, and there's this normalized thing as well, which I'll talk about in a second. So we can look at the graph of the Poisson distribution and see, well, actually, when the rate is 10, having 4 buses in a given hour is quite unlikely. But then again, you know, Sunday is just one of the 7 days, so it's quite unlikely that it was a Sunday in our prior assumption. So we need to do a calculation to figure out the answer. I'm using a Poisson distribution here. I'm assuming that buses are Poisson distributed. That's to say they're coming independently of each other. So let's assume there's no timetable. Maybe you've been to the UK. Let's assume there's no traffic lights or things causing buses to clump together and stuff like that. More than they would in a normal Poisson process. Okay, so in a normal informal statistics notation, you would just say something like this, that Sunday is Bernoulli distributed, the observation point y is Poisson distributed, and then you'd say y is 4, as I said a second ago. Okay, how do we solve this problem? Well, the simplest way is to run this program through. And what do? We've got 5 lines in the program. Let's talk about the second, third, fourth and fifth line first. So we first randomly pick which day it is, and we just toss a 7-sided dice, and that tells us whether it's a Sunday or not. That's our prior belief. And then we randomly simulate the bus service. And this gives us a number of buses coming by in a given hour. And it's going to give us more buses when it's a weekday than when it's a Sunday. And now we drop all the threads which didn't match with our observation. So we're going to run this thing thousands and thousands of times. And those things where we didn't get exactly 4 buses, we're going to drop. And then we're interested to know what proportion of the threads that we haven't rejected have Sunday as the day. Okay, so we run through thousands of times, drop the threads where there aren't 4 buses, and then count what proportion of the threads have the day as Sunday. Okay. A second thing we might do is to just do a pen on paper calculation. This is what you would do in high school. So that's not always possible with statistical models, but it is possible with this one, and let's have a go at it. So there's a 7th chance that it's a Sunday, and there's the likelihood of there being 4 from a Poisson distribution with the rate 3 is 0.17. That's over here, 0.17. And so we multiply the two things together and we get 0.024. When it's not a Sunday, when Sunday's false, then the likelihood is this thing here, which is much smaller, 0.019. And we multiply that by 6/7, which is the probability that it's not a Sunday, and we get 0.016. Okay, so but those two numbers, 0.024 and 0.016, don't sum to 1, so they're not a probability distribution. They sort of form a measure that's unnormalized. And the thing to do now is to divide by a normalizing constant, which is the sum of 0.024 and 0.016, which is roughly 0.04. I'm rounding all of these numbers a little bit. And so we end up with a posterior distribution, which says that the probability of it being a Sunday is 0.6. So it is more likely that it's a Sunday, if those of you who maybe guessed that, but it's not guaranteed at all from the observation that I've made. So what we're doing here is we're calculating with Bayes' law, and I think of Bayes' law as, I think of probabilistic programming as kind of Bayes' law plus programming constructs. So Bayes' law says that we calculate the posterior by noticing that it's proportional to the likelihood multiplied by the prior. The prior is this thing that we assume in advance, and the likelihood it involves the data that we have coming in. So probabilistic programming is sequential programming plus 3 constructions for these 3 things. Sample, which we've seen a lot of in the generative models, observe, which records a likelihood, and normalize, which calculates a normalizing constant given the likelihood and the prior. And that's the expensive thing to do. It's often just done at the top level. In some languages it's called different things like run query, do query, infer, and so on. So we talked about Monte Carlo simulation with rejection, where we throw away the things that don't we run a generative model and throw away the things that don't match what our observations are. But we can do slightly better than that. It's very wasteful. We'll end up rejecting most of the threads in this buses example because they don't match. They don't have 4. There aren't exactly 4 buses on those threads. So to do better than that, we could do Monte Carlo plus weighting. And it's very similar. We run through the program again thousands of times, but we don't throw away any of the runs. Rather, we weight the threads by their likelihood. So if it's a Sunday, we're going to weight the thread by the likelihood of the observation, which is 0.168. And if it's not a Sunday, we're going to weight the thread by the likelihood of the observation that there were 4 buses, which is 0.019. And now rather than counting the number of rejected or non-rejected threads, we're going to count the weighted proportion of threads where the day is Sunday. We don't throw anything away. Okay, so what we're interested in is the sum over all of the runs that we've done. There might be thousands of them. So each time we run, we're going to end up with a day with S, I, and a weight. And if SI is true, then we'll have a weight, WI, and that will, in this example, that will always be 0.168. and we'll divide that by the sum over all of the things that we saw when we were running and the weights that we saw. So those will be either 0.168 or 0.019. Okay, so this thing on the bottom is the normalizing constant, the total weight of all the runs, and we're interested in the proportion, the weighted proportion of threads that had the day being Sunday. Now let's make the story a little bit different. Instead of saying that I looked out the window for an hour and counted how many buses I saw, let's say I waited 15 minutes for a bus. I went to the bus stop and I waited 15 minutes. Is it a Sunday? Well, the gap between points in a Poisson process is exponentially distributed. So here I've plotted the exponential distribution with rate 10 and with rate 3. So again, we can look at what's the likelihood of that happening. Okay, so I've changed the line here in the program where I recorded the observation to now say I record it from the exponential distribution instead of from the Poisson distribution. Well, now we can no longer do rejection sampling because the probability of actually getting a 15-minute gap is 0. Okay, if I run a simulation of the bus network, I'll never end up, or almost never end up, with a 15-minute gap exactly between buses. The weighted method works absolutely fine. I can weight my threads by whatever these numbers are here, the likelihood of the exponential distribution at the 15-minute point, and that works absolutely fine. So the weighting method works very well. Maybe you're thinking what I should be observing really is not a 15-minute precise number, but rather some interval around 15 minutes plus or minus epsilon. Well, it turns out that if things are sufficiently continuous, then as epsilon goes to 0, that rejection sampling method tends towards giving the same answer as the likelihood, the weighted simulation method. Okay, so because I'm going to focus on this weighted simulation as a kind of a gold standard for implementation, let's actually change our notation to be more precise. And so what I'm doing then inside the probabilistic programming language, I have this stuff for generative models where I can draw from distributions, but I also can weight a thread. And so I'm going to add a new construction to my language called score, and score takes an argument which is a real number, a positive real number. And I'm typically going to call score with a probability density function evaluated at an observation point. Of course, I'm free to use score if I add it as a construct however I like. It doesn't really change the language expressivity, but it's just quite nice to be explicit about what happens with observations and weighting and scores. Okay, so I'm going to, instead of writing observe, I'm going to write score from now on. Okay, so let's have a look at this from the perspective of the Bayesian linear regression problem that we were talking about in the first part of this tutorial. So in the Bayesian linear regression problem, we're talking about fitting a line to some points and we want to get back a posterior distribution. And I set it up as a generative model to start with. So we had A, B, V, Y3, Y4 as all just as parameters of the same kind of status. But of course, Y3 and Y4 are observed data as opposed to parameters we want to infer. So now we can write this as a probabilistic program with the observe command inside, saying observe Y3 and observe Y4. And again, they come from normal distributions with the mean such as A3A plus B, and so on. Okay, so that's a probabilistic program for Bayesian regression. Now let me just rewrite it using the score command. So now I'm going to say score the run by either the normal probability density function with Y3 or the normal probability density function with Y4, okay, to record both of those observation points. And of course, there would actually be 7 score commands in the program, and you might use a for loop again to describe them all. Okay. Now, when we draw a graphical model, it looks something like this picture at the bottom of the page, where now instead of just having probability kernels, I have score nodes. You might wonder now with these score nodes whether it's still okay to do topological transformations of the picture. Indeed it is, but that's something that needs to be checked because these score things are no longer probability kernels. Let me talk a bit more about what they are. Okay. Before we do that, let's look at why we need to take a bit of care over the normalizing constant. So suppose I said I observed -4 buses in a given hour. Well, that's impossible. Doesn't even make sense to say that there were -4 buses. And so in rejection sampling, all the runs will be rejected. In the weighted simulation, all the runs will have a weight 0 because the likelihood is 0. And so the normalizing constant will be 0. Finding out whether the normalizing constant is 0 is in general a difficult problem. Here's a little program. Suppose I include in my language a Turing machine simulator. Then what I could do is the following. Draw a number from a Poisson distribution, call it k, so that gives me some number from 1 upwards, integer. And then I run my Turing machine. If it terminates after exactly k steps, I'm going to score that run with a 1, otherwise I'll score the run with a 0. And now the normalizing constant is going to be 0 if the machine doesn't terminate, and it will be something else otherwise. 1 otherwise. And indeed, to find a posterior for this probabilistic model will tell us exactly whether or not the machine terminates and how many steps it's going to take. So that gives you an idea of why inference is hard. Now, a Monte Carlo simulation will always converge to the true posterior. It's just that we don't know when it will converge. Okay, here's another problem, another program that illustrates a problem where the normalizing constant becomes infinity. So I haven't got a story behind this one, but it's a very similar shape to the problems with buses and so on that we've seen so far. So again, I'll draw a k from a Poisson distribution. I've drawn the density for the Poisson distribution over here. It's a distribution over positive natural numbers, so it has this kind of shape. And then I let the rate, I've chosen this very, very carefully, be k factorial times e. And then I observe 0 coming from an exponential distribution with that rate. In other words, I score my run with that rate. So I'm going to score my run by this thing here. It turns out that rate is the inverse of the density of the Poisson distribution. And so what we have now is that any natural number could come up and the normalizing constant is infinity. So this distribution, without trying to normalize, would describe a measure on the natural numbers, just as any unnormalized probability does, and it's the measure in which every natural number is, let's say, equiprobable. So every natural number has the same mass in the measure. Okay? So this is the counting measure on the natural numbers. And there's no way to normalize that into a probability measure. So here I'm simulating a geometric distribution using a Poisson distribution. So I draw k from a Poisson distribution. I score my run by this funny thing, k factorial times e, 1 over the density of the Poisson distribution. And then I score it again by a half to the k. The net result is the same as drawing from a geometric distribution, which has density 0.5 to the k. Okay, so that's a common way, maybe not this particular very specific example, but a common way to simulate distributions from other distributions. Okay. Similarly, we can define the Lebesgue measure on the real numbers as follows. Well, using this program here, I've done a very similar trick, and it's going to give us the measure which assigns to every real number 1. So that's not normalizable. Again, it's very useful to use as a sort of a base measure for things, and so it's quite useful in probabilistic programming for important sampling and so on, but it's not, it doesn't have a normalizing constant that you can divide by. Okay. Now, the Lebesgue measure is okay to have as part of programs, and so is the counting measure on the natural numbers, but things get hairy when we have the counting measure on the real numbers that assigns to every set of real numbers, every measurable set of real numbers, it's either infinity or the natural number of the number of points it has in it if it's finite. And that's for the following reason. Here I've written 2 programs and they're just the same but reordered. So in the first program I've said S draw S from the Lebesgue measure, and then draw R from the counting measure and ask whether R is equal to S. Now, if I draw R from the counting measure and I ask is R equal to S, well, the result is going to always be a distribution over true and false, which is always true. Okay? So I can always draw something from a counting measure to make R equal to S. It's counting the number of points in the set which are equal to S, and that's 1. Okay, so that's like a Dirac distribution at true. And so if I integrate over the Lebesgue measure the Dirac distribution at true, I again get the Dirac distribution at true. Whereas at the bottom program here, I'm drawing something from a Lebesgue measure, and then I'm asking whether R is equal to it. And if we forget about where R came from for a second, R is never equal, almost never equal to something from a Lebesgue measure. So the law of this program is the same as a Dirac at false. I'm counting how many things give me true and false, and I'm going to see that one thing gives me false, and that's it. Okay, so what we can see is that this kind of transformation that we've been talking about, where I have the Lebesgue measure and the counting measure, no longer holds if I allow the counting measure on the reals. And that's a real shame. It means we haven't got a multi-category, we haven't got a monoidal category, and we haven't got this handy manipulation that we want to have. Luckily, the counting measure on the real numbers is not definable in probabilistic programming language, even using score. And I'll explain to you why I know that now. Okay. And we do that by giving a semantics to a probabilistic programming language using S-finite kernels. So remember, normal distributions, inverse gamma distributions and so on are modelled as probability kernels that, given some parameters x, y, z, give us a probability measure on some space W. Let's just generalise that slightly to say that a finite kernel is allowed to sum to a little bit more than 1, but I want to have a bound k, a finite bound k, across all of the parameters of a finite kernel. So it's like an unnormalized probability distribution, but where the normalizing constant is fixed across is bounded across all parameters. And finally, an S-finite kernel is a countable sum of finite kernels. If you've got measure kernels, you can add them together, and they're again measure kernels. So an S-finite kernel is a countable sum of finite kernels. And so that's going to be something a bit like x times y times z, and giving me a measure on sigma w, but it might actually be an infinite measure. But it's not any old infinite measure that's allowed. It's got to be a countable sum of finite kernels. And that countable sum has to be the same across the parameter choices. Let me tell you some facts about S-finite kernels. Probability kernels are S-finite. Scores are sort of 1-point measures. So to give a score, well, it's to give, you've got some parameters x, and you give back a measure on score usually gives us back for each parameter a score between 0 and infinity, but that's the same as, okay, so a score is something that gives us for each parameter in x a number between 0 and infinity. That's the weight on the trace. But that's the same thing as saying for each x we give a measure on the single point space. And a measure on the single point space, or a parameterized measure on the single point space, is always S-finite. That's not so easy that's not immediate to see. You need to divide it into some finite parts in a uniform way and then add them together. Finally, S-finite kernels are closed under composition. So what that means is that we can use Fubini's theorem, as we did with probability kernels, to show how we can compose S-finite kernels and still get back S-finite kernels, so that we can do iterated composition and build diagrams like the kind that we've seen. And that all works because Fubini's theorem holds for probability kernels, also holds for finite kernels very straightforwardly. And a countable sum of finite kernels, well, countable sums commute with countable sums, and so we use that. So all told, S-finite kernels are the measure kernels that can be built from probability kernels and score. So they're exactly those ones that we can build from probabilistic programs. They then form a symmetric monoidal category. We can compose them, and there's also coproducts in there just as before, so we can do if, then, else, and clustering, and so on. Another characterization of S-finite measures, if you haven't seen them before, is that they are push forwards of sigma-finite measures. Perhaps you've seen sigma-finite measures before. Well, S-finite measures are just push forwards of sigma-finite measures. So the things that you have seen, really. The counting measure on the reals is not S-finite. I know that because I could use it to build things that didn't look like a monoidal category anymore. And so since S-finite kernels do form a monoidal category, it must be that the counting measure is not S-finite. You can prove it directly as well. And finally, a fifth thing is that there's an open problem about S-finite kernels, and that is, do they form a Kleisli category? So we know that the probability kernels form a Kleisli category for the Giry monad. Do S-finite kernels form a Kleisli category for some monad of measures? We know that every distributive symmetric monoidal category embeds in a Kleisli category, but what we don't know is whether this one is a Kleisli category. Okay, so I've given you an overview of probabilistic programming from a perspective of category theory, and we've talked about several things. We've talked about the distributive monoidal category of probability kernels being a good place to do generative models. Then we've talked about conditioning, and I looked at a particular way of doing conditioning by weighting by likelihood scores, and that gives us unbounded measures. Then I looked at a category of S-finite kernels, which explains in a compositional way what happens with conditioning. Let me say a few words about directions now. So I think there's some points I want to make on this slide. So I've talked about conditioning by likelihoods. There are other ways of dealing with this. One way is to set up the whole generative model as some kind of likelihood function or some kind of density function. And that's how it works in Staton. So you have a function which is actually smooth so that you can run Hamiltonian Monte Carlo simulation over it. Another interesting thing is to try to bring back together. So I haven't talked about how inference algorithms work at all. They're going to use the likelihoods, but they're going to do much better than a weighted Monte Carlo simulation in practice. I'll finish up there with this slide again. Probabilistic programs allow us to build complex models using ideas from programming languages in a way that makes the statistical models easy to write and easy to compose. We talked a little bit about inference, but we could talk a lot more about it. But since this is a categorical thing, not an inference workshop, I won't do that now. And I hope you can sort of see that we start to glimpse a synthetic measure theory where we're not too worried really about sigma algebras and so on. Rather, we're interested in objects of categories and morphisms and the ways that they compose. So thanks so much for watching, and thanks to Rory and Tobias for the invitation and for organising this event. Just send me an email, any questions, or we can chat on Zulip. Thanks a lot. See you.